All right, we're back. We're moving on. We've gotten through the whole thing of atoms, and now we're moving on to nuclear. And then tomorrow we'll actually do half-life. So today we're just looking at nuclear and kind of what is nuclear science. All right, so the first thing is, what is a nuclear reaction? And basically, these aren't that common. They do happen naturally, but they're not that common. But basically, what you're doing is you're actually changing the atom's nucleus. And when an atom's nucleus has lots and lots of energy stored in it, so when you're changing the nucleus, you usually release a lot of energy, and you kind of have to be careful because it can be really dangerous. If you think back to the atom we talked about, the nucleus is made of protons and neutrons. And remember, these protons are all positive, so they should be repelling each other. But you have these neutrons in there to kind of help hold the actual nucleus together. What happens though is when you get too large, you start having this thing where you just have too many neutrons. There's just so many more neutrons than protons that you actually become fairly unstable. And when you have this instability, you're called radioactive, which means that your nucleus is actually going to change. Every single element on the whole periodic table has at least one radioactive isotope. So again, this is something that's natural. This is something that naturally occurs. It's just something that little too many neutrons we have to deal with. When you get on the periodic table anywhere above 83, everything is radioactive. There's nothing that's not radioactive. There's just too many neutrons, and they kind of start falling apart. And if you look at this picture down below, this is a nuclear reaction they kind of did a depth charge in the ocean, and you can see how much energy is being released, because that is a pretty big ship that's there, and you can see that's a really, really large explosion. All right, so you have these nucleuses that are unstable, and you're trying to get rid of something. This nucleus, kind of like if you're sick, maybe you throw up, maybe you just don't eat for a while, but basically what's happening with the nucleus is the same thing. They're trying to basically become more stable to not be sick. So there's a couple different things that can come out. The first thing is something you're really familiar with, is a proton, and we all know that a proton has a charge of +1. And when we write a proton, we write a little p, and we say that it has an atomic number of 1, and it has a charge of +1, basically. Oops, wait, no, I don't want to write that. So we write this, we just have a p, and he has a mass of 1 and an atomic number of 1. Another thing that can happen is they can spit out a neutron, because neutrons are in the nucleus. So they can have a charge of 0 because they're neutrons, and a neutron is a little n, and we say he has no atomic number, so he's a 0, and he has the mass of 1. So those are things that normally would come out of a nucleus, proton and a neutron. If I was going to shoot you with protons, you would be like, that's okay, I'm going to hold up a couple of pieces of paper, and you would be able to stop those protons coming at you. If I was going to shoot neutrons at you, you'd have to work a little harder, and you'd actually have to hold up a little bit of lead, because they're a little harder to stop. So those are things that naturally are in the nucleus, these protons and neutrons, they can come out. The bottom three are things that aren't naturally there, that the nucleus is going to kind of get rid of artificially. So the first thing is called a beta particle, and it's like an electron. It has a charge of -1. It is not an electron. It just looks like an electron to us. There are not electrons in the nucleus, but this is what we call it. It looks like one. There's two ways you can write it. You can write 0, -1, and write a little beta, which is Greek. Or you can write 0, -1, and write a little e for an electron. It's, again, not an electron. It just looks like it. And if I have a beta gun and I'm shooting at you, those people that you thought were crazy, when they wear aluminum foil, that actually would stop the beta particles. So they're maybe not so crazy after all. The next thing is an alpha particle. These are really heavy. And they do have a charge. They have a +2 charge. And these guys have two ways you can write them. You can either write 4 for the mass, 2 for the atomic number, and write a little alpha, which looks like a little fishy. Or you can write 4, 2, and then write an HE. Because if you look at this over here, the alpha particle is essentially a helium nucleus. So you can write either one of those. Either one's fine. If I was going to shoot you with an alpha particle, you would just hold up a piece of paper, or you would say, okay, my skin's going to stop it, so it doesn't even matter. And then the last type is called gamma rays. These are pure energy, and they can be potentially the most dangerous because it's just pure energy coming out. They have no charge, and the way you write these is you write a gamma, which is this symbol right here. It looks kind of like a fish swimming down. It has 0 mass and 0 atomic number. And these are the hardest to stop, where you need actually lead to stop those. So they are the trickiest ones to stop. You have a little picture in your notes that shows you that alpha is the biggest, and it's going to be the easiest to stop. So all you have to do is hold up a piece of paper and it'll stop it. Beta is a little smaller, it's harder to stop. So this one you need aluminum foil, and then the last one at the bottom is gamma. It's going to be the hardest to stop, and you're going to need the lead shielding. So if you think of those bomb shelters, that's what they're talking about. All right, so there's different types. The first type is called radioactive decay. This is natural, this happens, and it's spontaneous. So again, remember, you have this nuclear force that's holding the nucleus together, but when you have this nucleus, if you have a nucleus that's just too big, it's just too massive, they're going to become unstable, and they're going to naturally emit one of those 3 types of radiation, the alpha, the beta, and the gamma. And this is called your good old radioactive decay. So right here, radioactive decay. Down here, this is called a cloud chamber. What a cloud chamber does is it lets you see the trail of the actual radiation. You don't actually see the radiation, you see where the radiation has been. And you can see that they kind of make little spirals and all that kind of good stuff. All right, so how can you actually write this? How can you actually show this? There's a couple different ways you can do it, and it's going to depend on the type. Basically, what happens, though, if you think of the law of conservation of mass, is everything has to be, if we start with a certain amount, we're going to have to end with a certain amount. So if you look right here, we started off with radium, and its mass, when it started, was 226, and its atomic number was 88. So what happens is there's an alpha decay. This is unstable and it falls apart. So it spits out an alpha. And over here is an alpha. And we have our little alpha symbol. You could write HE there. That's fine. But this has an alpha symbol. And we know that an alpha symbol has a mass of 4 and an atomic number of 2. What we have to do to figure out what this guy is over here is we have to say, okay, I can't lose this 226. So if I have 4... from the alpha, what plus 4 has to equal 226? And since you're very good at mental math, you all know that it would be 222. And basically it comes down to 222 plus 4 equals this 226. That way we're obeying the law of conservation of mass. We're not losing anything. We do the same thing for the bottom. The alpha particle has an atomic number of 2. So I say what plus 2 will give me this 88. And that's where my 86 comes from. And then the last thing you do is figure out what in the world is this element. So you look up number 86 on the periodic table, and he is radon, or Rn. So if we do the next one, the very top is 185, and he's going to spit out an alpha, which means his mass is 4. So we say what plus 4 will give us 185, and you're all really smart. So we have 181. Again, 181 plus 4 gives us this 185, and they need to be the same so that we're not creating or destroying matter. And then we do the same thing for the bottom. What plus 2 is going to give us a 79, and it's 77. So now that's the mass, 181. 77 is its atomic number. So now we look it up on the periodic table. We look up number 77. It's iridium. So it's IR. And that's how you write a balanced nuclear equation. And we'll get to other types of equations too, but this is a nuclear. Second one is beta. You have to be a little careful with beta. They're kind of easy, kind of tricky. So we have this. We have our carbon, and we say, okay, the beta over here is 0. So really high-level thinking right here. What plus 0 gives me 14? So we're hoping we're going to write down 14. And then this is the one you have to be careful of. What plus minus 1 gives me 6, That is 7. So you have to be careful with that guy. Our mass is 14, our atomic number is 7, so we look him up, and he is nitrogen. And then last guy down here, same thing. We say what plus 0 gives us 25. And we're again hoping you say 25. And then we say what plus minus 1 gives you 13. And that would be 14. And then you say, okay, what element is this? And he's Si, silicon. As we look up number 14 on that periodic table. All right. And last type is the gamma. And the gamma is really easy because if you look at gamma over here, they're both 0. So you say what plus 0 gives me 238, and you say 238. And you say what plus 0 gives me 92, still 92. So he's still uranium. You just have to make sure whatever you have on the left adds up to whatever you have on the right. And the same thing goes for the mass and the atomic number. All right, and then the last thing we're going to talk about today is transmutation. Transmutation is when something doesn't just naturally happen. So what we've been talking about are things that naturally are radioactive, they naturally fall apart. Transmutation is when we make them fall apart. So what happens is you have your nucleus, and then basically what you do is you make a new nucleus by actually hitting it and making it unstable. So what you do is you bombard a nucleus, or you hit it, with something. And what it does is it makes it unstable. And what you have is this unstable nucleus. And what happens is this unstable nucleus wants to fall apart, it wants to be more stable, and what actually happens is then you actually force a reaction to occur. And we'll look at that in 1 second because they're a little different because all the decay ones, there's only one thing on the left, and then there'd be 2 things on the right. If you look up above at that gamma, there's uranium on the left, and then there's uranium and gamma on the right. But if you look at a transmutation, that's not what it's going to look like. So if we look there. So what do they actually use this for? We'll actually look at a little video. If you remember that CERN thing that started up last year, the big particle accelerator, this is what they actually do there. They actually bombard things. So if you look at this, this is an example of a bombardment. You're going to have to be able to write these, and you're going to practice it tonight. So we have nitrogen. Has a mass of 14 and an atomic number of 7. He's stable. He's not falling apart. We take an alpha particle, this guy right here, 4,2 helium. Remember, you can write helium, or you can actually write the alpha symbol. It doesn't matter. So we hit him with this. So there's 2 things on the left. And that means we're bombarding it. What happens is they go together, so we just add it up. So we do 14 plus 4, we get an 18. And then we do 7 plus 2, and we get a 9. We look that up, and when it turns out he's fluorine. What's going to happen then, though, is he's going to fall apart. And in a normal bombardment problem, I'm going to tell you what he falls apart into. But what he falls apart into here is he forms a weird oxygen thing, so I would have to tell you one of these. So say I tell you he forms 17, an oxygen molecule with a mass of 17. You would have to figure out what would this guy be. Only difference, same rules apply. It's just that you're going to have 2 things on the left, 2 things on the right, and you have this unstable nucleus in the middle. And then in a sec, you're going to actually watch a really corny little rap about that CERN place in the particle accelerator.